that we'll use is this plastic ball, and we'll project it with this cannon. This cannon, this device has a spring in it, and I'll just hold it here so you can see it. And I can force the spring down, and it will stay in place there. So the spring is compressed at this point. I'll push the cart along this level track. Now my table's not quite level, so I put some cardboard here to make sure that it was level. So you can see the cart doesn't move on the track. The other thing that I need is to release the ball, and for that purpose I have an automatic release, which is a photo gate. The photo gate is this device on the side, which has a slot in it. There's an infrared beam passing across it. If I break that infrared beam with something, then that will release the ball. What I'll break it with is this piece of cardboard. So I'm going to mount this cardboard on this clamp right here at exactly the level of the photo gate, and double check. Now when I pass it through, let me just show you how this works. When I pass it through the photo gate, it releases the ball. So I'll get the flag in position, line it up, and we're set to go. Ready the cart. I'll give a push, and I'll stop pushing before the flag actually passes through the photo gate. And as you can see, the ball fell right back down into the cannon. Let's take another look at that. Ready? Right back down in the cannon before I actually caught it over here. So what that is showing us is that the ball continues traveling horizontally with the same speed that the cart has. The cart doesn't slow down, the ball doesn't slow down, and since they're both moving horizontally together, the ball comes right back down in the cart. And the fact that gravity was acting on the ball all the time and making it slow down on the way up and speed up on the way down had absolutely no effect on that horizontal motion. This will be an experiment to measure the speed of sound. Now we know that speed is the change in distance over the change in time. So our method is going to be to measure how far sound travels in a certain amount of time, and then take the distance it traveled and divide it by the amount of time. Now the way this experiment is usually done is over a much greater distance than we're going to be using in the laboratory here. For example, you might station people at opposite ends of a football field. And at one end of the field, you have somebody smashing two trash can lids together. And at the other end of the field, you have someone with a stopwatch who times how long it takes from when that person sees the trash can lids actually contact each other to when they actually hear the sound. And there is a noticeable time delay there. Now, since we are just going to be working over the space of this table, we don't have those long distances. We're going to have a much shorter period of time, which you won't be able to use a stopwatch. We'll have to use a different way to measure the time, but we will be able to do that successfully. Here's some of the equipment that we'll be using. One piece is this flash unit. This is just a standard flash that you might put on top of a camera. Let's give it a flash here. This device is not quite so standard. It's a sound actuated trigger. It's composed of a microphone right here. Inside is a little audio amplifier, and the way it works is I'll turn it on here, and when it receives a sound, it automatically sets off that flash. Okay. And we have two of those. Over here is another flash with its own sound trigger. I'll turn that one on. Okay. Now here's basically the plan of the experiment. If I stand right here and produce a sound, it will set off this flash first because it reaches this microphone first. And then the sound will take some time to travel along here, and it will set off the second one. Let's try that right now. You keep an eye on the two flashes. Once more. Now I'm sure you couldn't tell that there was a time delay between those two flashes. The time interval is just too short. So that means we're going to have another piece of equipment in order to measure that short time interval. So I'll show you that piece of equipment next. This is the device that I'll use to measure the short time intervals that we're going to have in this experiment. Now there's nothing special about it. It used to be a fan, one of these clip fans that clip to the table. I took off the fan blades, and replaced it with this cardboard disc painted black with a white line on it. And you can think of this as a high-speed clock. And so the white line is the hand of our clock, and let's see how fast it goes. It goes so fast that normally you can't actually see it turning. But with the flashes, we will be able to see the line at a particular instance of time. Let's see that right now. So I'll begin by turning the flashes around now to face the disk. I'll turn on this trigger, and you can see that when the flash goes off, you get a very sharp image of the line on the disk. And that's because this flash is only lasting about a 30,000th of a second. Let me turn the other one on. And now if I make a sound right here, you'll see two images of the hand on the clock. And that's because when the sound reaches this microphone, the flash goes off and you get one image. And then time passes and it reaches the other microphone and that flash goes off and you get the second image, and the disk will have turned during that time far enough so that you can see the angle between them. And that angle, we will find, will be a measure of the amount of time that passed from one sound trigger to the other one. Now, in order to use the clock to measure the amount of time, we will need to know the angle between the two images of the clock hand, but we need to know something else. We need to know how fast that clock is turning. To find that out, we'll use a stroboscope and use a method like was shown to you in a previous clip. I'm going to set the stroboscope for a frequency of 50 flashes per second because I want to make the disk go around 50 times per second. I've got a variable speed control here, and I'll adjust that. And I get, that should be pretty nearly 50 rotations per second. It's a little bit different, but it's close enough for what we're doing here. It'll change slightly. So now we know the frequency of the motor. I'll make one more addition to the equipment. I'll put colored filters on the flash units. A green filter for the left flash and a red filter for the right flash. The reason for this is that the hand that shows up on the clock for each of the flashes will be a different color, and so we'll easily be able to distinguish between the flashes and see which one went off first. Let's just take a look at that. I'll make a sound here, and you can see both a red and a green image on the disk. You can also tell which one went off first because the disk is rotating clockwise, and when you look at the hands, the green one appears in that particular case at about the 1 o'clock position and the red at about the 2 o'clock position. The red one went off a little bit later because sound had to travel further to reach it. Now, to test the triggers, to make sure that they respond in the same way, I put them both together and make the sound out front so that the sound travels the same distance to each microphone. In that case, the two images of the hand should be on top of each other, and they should look neither red nor green, but probably white. And you can see that's the case. Now we're ready to do the experiment. I'll begin by placing the left trigger at the 10 centimeter mark on the meter stick, and the right trigger at the 70 centimeter mark. That means the distance between them is 60 centimeters. I'll produce a sound with the two blocks out here on the end in line with the two microphones. That's so that the time between the flashes will correspond to the distance between the microphones. Here goes. Now you can see the angle is quite a bit less than the 90 degrees that we're trying to achieve. So what I need to do is move the triggers farther apart. So I'm going to put this one at right in the middle there now at 100 centimeters. So the distance between them now is 90 centimeters. Here we go again. Still quite a bit less than 90 degrees. Let's make a bigger change. I'll go out to 140 centimeters there, so the distance now is 130 centimeters between sound triggers. Still a little bit less than 90, but we're getting close. Let's try almost the other end of the table, 180. So the difference between them now is 170 centimeters. That looks pretty close to 90 degrees, so let's use those particular results. So our data then is the distance between the sound triggers is 1.70 meters. The angle on the disc is 90 degrees, and the frequency of the disc is 50 rotations per second. So we'll now use that information to calculate the speed of sound. In the last experiment, we measured the speed of sound. We did that by using a high-speed clock to measure short time intervals. In this experiment, we're going to do things just a bit differently. Now that we know the speed of sound, we're going to use that particular value to measure short time intervals. And the short time interval that we're going to measure is the amount of time it takes this balloon to pop. From the instant that I prick the balloon with this pin until the balloon is pretty much completely gone, that's the amount of time that we're going to determine. You might call that the lifetime of a bursting balloon. The experiment will use some of the same equipment as in the last experiment. A sound trigger connected to this flash unit, and then the 2 meter sticks that we'll use to measure distance. To begin the experiment, I'll be putting the balloon right here at the 0 mark of the meter stick. I'll pop it right at the front. It won't take very long for the sound to travel from the point where I prick the balloon to the sound trigger. In that amount of time, the balloon won't rip very far. It will still be pretty much an intact balloon. But then I'm going to move the balloon further and further down the meter stick. And the further I move it while keeping the sound trigger in the same place, the longer it will take sound to travel from the balloon to the trigger, and so more time will elapse. About how much time are we talking about? Well, from the last experiment, you probably found that the speed of sound was about 340 meters per second. Now, that's also the same thing as 340 millimeters per millisecond. Now, it's useful to think of it in those units because of the fact that we're going to be dealing with very short time intervals that are on the order of milliseconds rather than seconds. For example, if I move the balloon from the 0 mark to about 1/3 of a meter, well, 1/3 of a meter is 33 centimeters, and that's 330 millimeters. If the speed of sound is 340 millimeters per millisecond, that amount of time for sound to travel this far is just about 1 millisecond. So if, for example, the balloon were, let's say, 2/3 of the way down the meter stick, and we popped it, and we saw that the balloon was pretty much gone at that point, we could say, well, that took about 2 milliseconds because each third of a meter is a millisecond of time. Okay? So we'll use that in order to figure out the lifetime of this bursting balloon. So let's begin, and we'll do a series of 4 bursts, one at 0, one at 1/2 meter, and one at 1 meter, and one at 1.5 meters. And then we'll see what results we get from those. So let's begin with the first one. Here goes. So on the freeze frame, you saw that the balloon had split just a very short distance up the front of it, and that's because the amount of time it took sound to travel from the point of the rip to the microphone on the sound trigger was very short. Next, I'll move the balloon, the next balloon, 1/2 meter down the stick, and we'll do it again, but I'm going to move my flash down just a little bit so it's closer, but I'm keeping the sound trigger in the same place. Okay, let's try this one. Well, in that particular shot, you saw that the balloon was ripped completely up the front and actually ripping on the back. So the balloon was about half gone. Let's keep moving on down the meter stick. Well, that time the balloon was pretty much gone, but it still had a little bit of shape of the balloon. So let's move down another 1/2 meter for the final shot. Well, in that last shot, you can see that the balloon was almost completely gone. There was just a little piece left, and it was completely collapsed. So we can say that the lifetime of a bursting balloon, at least the balloons that I'm using here, is about the amount of time it takes sound to travel a distance of 1.5 meters. So knowing the speed of sound and that distance, you can calculate the amount of time it takes a balloon to burst. The device that I have here is a generator. Let's see what parts it has. I can turn the crank here. When I turn the crank, what it does is turn an armature inside. Now, an armature is a coil of wire that's specially wound, and it turns in a magnetic field. And the purpose, of course, as you know from generators, is to generate electrical current. Now, you can't see the armature inside there, so I'm just telling you about it. Also inside here are a series of gears, and the purpose of the gears are to increase the rate of rotation of the armature compared to the rate of cranking. So I can crank slowly, and I could get a very rapid rotation inside the armature. The output of the generator comes through these two wires. So if I clip this to something external, such as a light bulb, I will get electrical current going through the light bulb. All right. Before I do that, I want to show you another function of this device. This can also act as a motor, which basically acts the reverse as a generator. As a motor, as you know, what we do is we take electrical energy or electrical current, and we convert it to mechanical energy of rotation. All right. So to make it work as a motor, I just take my clips and I connect them to a battery. And when I do, current will pass through the armature inside here. That armature is in a magnetic field, so the magnetic field exerts magnetic force on the current, and that produces a torque which turns the crank. So let's see that happen. All right, so that's the motor. All right, so let's move the battery pack aside, and now we're going to see it work in the reverse as a generator. So this time I will be inputting mechanical energy of rotation, and the result will be electrical energy as an output. So we'll connect this to a light bulb. And crank away. And a little bit of cranking, you get some light from the bulb. A lot of cranking, the bulb is very bright. So as I crank faster, I was generating greater current. And as you know, the power dissipated by the bulb is the square of the current times the resistance of the bulb. So greater current means greater power dissipation, hence more light. All right. Now there's something else interesting going on with this that you couldn't see, but I could feel it, and I want to talk to you about that. When I turn this, I feel a mechanical resistance to my turning. Something is pushing back on my hand. And that depends